Magnetometers are measurement instruments used for two general purposes: to measure the magnetization of a magnetic material like a ferromagnet, or to measure the strength and, in some cases, the direction of the magnetic field at a point in space. The first magnetometer was invented by Carl Friedrich Gauss in 1833, and notable developments in the 19th century included the Hall effect, which is still widely used. Magnetometers are widely used for measuring the Earth's magnetic field and in geophysical surveys to detect magnetic anomalies of various types. They are also used in the military to detect submarines. Consequently, some countries, such as the United States, Canada and Australia, classify the more sensitive magnetometers as military technology, and control the distribution. Magnetometers can be used as metal detectors. They can detect only magnetic metals, but can detect such metals at a much larger depth than conventional metal detectors. They are capable of detecting large objects, such as cars, at tens of meters, while a metal detector's range is rarely more than 2 meters. In recent years, magnetometers have been miniaturized to the extent that they can be incorporated in integrated circuits at very low cost and are finding increasing use as compasses in consumer devices such as mobile phones and tablet computers. Laboratory magnetometers. Laboratory magnetometers measure the magnetization, also known as the magnetic moment, of a sample material. Unlike survey magnetometers, laboratory magnetometers require the sample to be placed inside the magnetometer, and often the temperature, magnetic field, and other parameters of the sample can be controlled. A sample's magnetization is primarily dependent on the ordering of unpaired electrons within its atoms, with smaller contributions from nuclear magnetic moments, Lama diamagnetism, among others. Ordering of magnetic moments are primarily classified as diamagnetic, paramagnetic, ferromagnetic, or antiferromagnetic. Measuring the magnetization as a function of temperature and magnetic field can give clues as to the type of magnetic ordering, as well as any phase transitions between different types of magnetic orders that occur at critical temperatures or magnetic fields. This type of magnetometry measurement is very important to understand the magnetic properties of materials in physics, chemistry, geophysics and geology, as well as sometimes biology. Squids are a type of magnetometer used both as survey and as laboratory magnetometers. Squid magnetometry is an extremely sensitive absolute magnetometry technique. However, squids are noise sensitive, making them impractical as laboratory magnetometers in high DC magnetic fields and in pulsed magnets. Commercial squid magnetometers are available for temperatures between 300 mK and 400 kelvins, and magnetic fields up to 7 teslas. Inductive pickup coils. Inductive pickup coils measure the magnetization by detecting the current induced in a coil due to the changing magnetic moment of the sample. The sample's magnetization can be changed by applying a small magnetic field, as occurs in capacitor-driven pulsed magnets. These measurements require differentiating between the magnetic field produced by the sample and that from the external applied field. Often a special arrangement of cancellation coils is used. For example, half of the pickup coil is wound in one direction, and the other half in the other direction, and the sample is placed in only one half. The external uniform magnetic field will be detected by both halves of the coil, and since they are counterwound, the external magnetic field produces no net signal. VSM. VSM detect the magnetization of a sample by mechanically vibrating the sample inside of an inductive pickup coil or inside of a squid coil. Induced current, a changing flux in the coil, is measured. The vibration is typically created by a motor or a piezoelectric actuator. Typically the VSM technique is about an order of magnitude less sensitive than squid magnetometry. VSMs can be combined with squids to create a system that is more sensitive than either one alone. Heat due to the sample vibration can limit the base temperature of a VSM, typically to 2 Kelvin. VSM is also impractical for measuring a fragile sample that is sensitive to rapid acceleration. Pulsed field extraction magnetometry. Pulsed field extraction magnetometry is another method of making use of pickup coils to measure magnetization. Unlike VSMs where the sample is physically vibrated, in pulsed field extraction magnetometry, the sample is secured and the external magnetic field is changed rapidly, for example in a capacitor-driven magnet. One of multiple techniques must then be used to cancel out the external field from the field produced by the sample. These include counterwound coils that cancel the external uniform field, and background measurements with the sample removed from the coil. Torque magnetometry. Magnetic torque magnetometry can be even more sensitive than squid magnetometry. However, magnetic torque magnetometry doesn't measure magnetism directly as all the previously mentioned methods do. Magnetic torque magnetometry instead measures the torque tau acting on a sample's magnetic moment mu as a result of a uniform magnetic field B. Tau equals mu times B. A torque is thus a measure of the sample's magnetic shape anisotropy. In some cases the sample's magnetization can be extracted from the measured torque. In other cases, the magnetic torque measurement is used to detect magnetic phase transitions or quantum oscillations. The most common way to measure magnetic torque is to mount the sample on a cantilever and measure the displacement via capacitance measurement between the cantilever and nearby fixed object, or by measuring the piezoelectricity of the cantilever, or by optical interferometry off the surface of the cantilever. Faraday force magnetometry. Faraday force magnetometry makes use of the fact that a spatial magnetic field gradient will produce force acting on a magnetized object, F equals B. In Faraday force magnetometry, the force on the sample can be measured by scale, or by detecting the displacement against a spring. Commonly a capacitive load cell or cantilever is used because of its sensitivity, size, and lack of mechanical parts. Faraday force magnetometry is approximately 1 order of magnitude less sensitive than a squid. The biggest drawback to Faraday force magnetometry is that it requires some means of not only producing a magnetic field, but also producing a magnetic field gradient. While this can be accomplished by using a set of special pole faces, a much better result can be achieved by using a set of gradient coils. A major advantage to Faraday force magnetometry is that it is small and reasonably tolerant to noise, and thus can be implemented in a wide range of environments, including a dilution refrigerator. Faraday force magnetometry can also be complicated by the presence of torque. This can be circumvented by varying the gradient field independently of the applied DC fields of the torque, and the Faraday force contribution can be separated, or by designing a Faraday force magnetometer that prevents the sample from being rotated. Optical magnetometry. Optical magnetometry makes use of various optical techniques to measure magnetization. One such technique, Kerr magnetometry, makes use of the magneto-optic Kerr effect, or MOG. In this technique, incident light is directed at the sample's surface. Light interacts with a magnetized surface non-linearly, so the reflected light has an elliptical polarization, which is then measured by a detector. Another method of optical magnetometry is Faraday rotation magnetometry. Faraday rotation magnetometry utilizes nonlinear magneto-optical rotation to measure a sample's magnetization. In this method, a Faraday modulating thin film is applied to the sample to be measured, and a series of images are taken with a camera that senses the polarization of the reflected light. In order to reduce noise, multiple pictures are then averaged together. One advantage to this method is that it allows mapping of the magnetic characteristics over the surface of a sample. This can be especially useful when studying such things as the Meissner effect on superconductors. Survey magnetometers. Survey magnetometers can be divided into two basic types. Scalar magnetometers measure the total strength of the magnetic field to which they are subjected, but not its direction. Vector magnetometers have the capability to measure the component of the magnetic field in a particular direction, relative to the spatial orientation of the device. A vector is a mathematical entity with both magnitude and direction. The Earth's magnetic field at a given point is a vector. A magnetic compass is designed to give a horizontal bearing direction, whereas a vector magnetometer measures both the magnitude and direction of the total magnetic field. 3 orthogonal sensors are required to measure the components of the magnetic field in all 3 dimensions. They are also rated as absolute if the strength of the field can be calibrated from their own known internal constants, or relative if they need to be calibrated by reference to a known field. A magnetograph is a magnetometer that continuously records data. Magnetometers can also be classified as AC if they measure fields that vary relatively rapidly in time, and DC if they measure fields that vary only slowly or are static. AC magnetometers find use in electromagnetic systems, and DC magnetometers are used for detecting mineralization and corresponding geological structures. Scalar magnetometers. Proton precession magnetometer. Proton precession magnetometers, also known as proton magnetometers, PPMs or simply mags, measure the resonance frequency of protons in the magnetic field to be measured due to nuclear magnetic resonance, because the precession frequency depends only on atomic constants and the strength of the ambient magnetic field. The accuracy of this type of magnetometer can reach 1 ppm. A direct current flowing in a solenoid creates a strong magnetic field around a hydrogen-rich fluid, causing some of the protons to align themselves with that field. The current is then interrupted, and as protons realign themselves with the ambient magnetic field, they precess at a frequency that is directly proportional to the magnetic field. This produces a weak rotating magnetic field that is picked up by an inductor, amplified electronically, and fed to a digital frequency counter whose output is typically scaled and displayed directly as field strength or output as digital data. For hand backpack carried units, ppm sample rates are typically limited to less than 1 sample per second. Measurements are typically taken with the sensor held at fixed locations at approximately 10 meters increments. Portable instruments are also limited by sensor volume and power consumption. PPMs work in field gradients up to 3000 nt per meter, which is adequate from most mineral exploration work. For higher gradient tolerance, such as mapping banded iron formations and detecting large ferrous objects, Overhauser magnetometers can handle 10,000 nt per meter, and cesium magnetometers can handle 30,000 nt per meter. They are relatively inexpensive and were once widely used in mineral exploration. 3 manufacturers dominate the market: GEM Systems, Geometrics and Syntrex. Popular models include G856, SmartMag and GSM18 and GSM190. For mineral exploration, they have been superseded by Overhauser, cesium and potassium instruments, all of which are fast cycling, and do not require the operator to pause between readings. Overhauser effect magnetometer. The Overhauser effect magnetometer or Overhauser magnetometer uses the same fundamental effect as the proton precession magnetometer to take measurements by adding free radicals to the measurement fluid. The nuclear Overhauser effect can be exploited to significantly improve upon the proton precession magnetometer. Rather than aligning the protons using a solenoid, a low-power radio frequency field is used to align the electron spin of the free radicals, which then couples to the protons via the Overhauser effect. This has two main advantages. Driving the RF field takes a fraction of the energy, and faster sampling as the electron-proton coupling can happen even as measurements are being taken. An Overhauser magnetometer produces readings with a 0.01 nt to 0.02 nt standard deviation while sampling once per second. Cesium vapor magnetometer. The optically pumped cesium vapor magnetometer is a highly sensitive and accurate device used in a wide range of applications. It is one of a number of alkali vapors that are used in this way, as well as helium. The device broadly consists of a photon emitter containing a cesium light emitter lamp, an absorption chamber containing cesium vapor, a buffer gas through which the emitted photons pass, and a photon detector arranged in that order. The basic principle that allows the device to operate is the fact that a cesium atom can exist in any of 9 energy levels, which can be informally thought of as the placement of electron atomic orbitals around the atomic nucleus. When a cesium atom within the chamber encounters a photon from the lamp, it is excited to a higher energy state, emits a photon and falls to an indeterminate lower energy state. The cesium atom is sensitive to the photons from the lamp in 3 of its 9 energy states, and therefore, assuming a closed system, all the atoms will eventually fall into a state in which all the photons from the lamp will pass through unhindered and be measured by the photon detector. At this point, the sample is said to be polarized and ready for measurement to take place. This process is done continuously during operation. This theoretically perfect magnetometer is now functional and can begin to make measurements. In the most common type of cesium magnetometer, a very small AC magnetic field is applied to the cell. Since the difference in the energy levels of the electrons is determined by the external magnetic field, there is a frequency at which this small AC field will cause the electrons to change states. In this new state, the electron will once again be able to absorb a photon of light. This causes a signal on a photodetector that measures the light passing through the cell. The associated electronics use this fact to create a signal exactly at the frequency which corresponds to the external field. Another type of cesium magnetometer modulates the light applied to the cell. This is referred to as a Bell blue magnetometer, after the two scientists who first investigated the effect. If the light is turned on and off at the frequency corresponding to the Earth's field, there is a change in the signal seen at the photodetector. Again, the associated electronics use this to create a signal exactly at the frequency which corresponds to the external field. Both methods lead to high-performance magnetometers. Potassium vapor magnetometer. Potassium is the only optically pumped magnetometer that operates on a single, narrow electron spin resonance line, in contrast to other alkali vapor magnetometers that use an irregular, composite and wide spectral lines, and helium with the inherently wide spectral line. Applications. The cesium and potassium magnetometers are typically used where a higher performance magnetometer than the proton magnetometer is needed. In archaeology and geophysics, where the sensor sweeps through an area and many accurate magnetic field measurements are often needed, cesium and potassium magnetometers have advantages over the proton magnetometer. The cesium and potassium magnetometer's faster measurement rate allows the sensor to be moved through the area more quickly for a given number of data points. Cesium and potassium magnetometers are insensitive to rotation of the sensor while the measurement is being made. The lower noise of cesium and potassium magnetometers allow those measurements to more accurately show the variations in the field with position. Vector magnetometers. Vector magnetometers measure one or more components of the magnetic field electronically. Using three orthogonal magnetometers, both azimuth and dip can be measured. By taking the square root of the sum of the squares of the components, the total magnetic field strength can be calculated by Pythagoras's theorem. Vector magnetometers are subject to temperature drift and the dimensional instability of the ferrite cores. They also require leveling to obtain component information, unlike total field instruments. For these reasons, they are no longer used for mineral exploration. Rotating coil magnetometer. The magnetic field induces a sine wave in a rotating coil. The amplitude of the signal is proportional to the strength of the field, provided it is uniform, and to the sine of the angle between the rotation axis of the coil and the field lines. This type of magnetometer is obsolete. Hall effect magnetometer. The most common magnetic sensing devices are solid-state Hall effect sensors. These sensors produce a voltage proportional to the applied magnetic field and also sense polarity. They are used in applications where the magnetic field strength is relatively large, such as in anti-lock braking systems in cars which sense wheel rotation speed via slots in the wheel discs. Magneto-resistive devices. These are made of thin strips of permalloy whose electrical resistance varies with a change in magnetic field. They have a well-defined axis of sensitivity, can be produced in 3D versions and can be mass-produced as an integrated circuit. They have a response time of less than 1 microsecond and can be sampled in moving vehicles up to 1,000 times per second. They can be used in compasses that read within 1 degree, for which the underlying sensor must reliably resolve 0.1 degrees. Fluxgate magnetometer. The fluxgate magnetometer was invented by H. Aschenbrenner and G. Gauss in 1936. A team at Gulf Research Laboratories led by Victor Vacquia developed airborne fluxgate magnetometers to detect submarines during World War II, and after the war confirmed the theory of plate tectonics by using them to measure shifts in the magnetic patterns on the sea floor. A fluxgate magnetometer consists of a small, magnetically susceptible core wrapped by 2 coils of wire. An alternating electric current is passed through one coil, driving the core through an alternating cycle of magnetic saturation, i.e., magnetized, unmagnetized, inversely magnetized, unmagnetized, magnetized, and so forth. This constantly changing field induces an electric current in the second coil, and this output current is measured by a detector. In a magnetically neutral background, the input and output currents will match. However, when the core is exposed to a background field, it will be more easily saturated in alignment with that field and less easily saturated in opposition to it. Hence, the alternating magnetic field and the induced output current will be out of step with the input current. The extent to which this is the case will depend on the strength of the background magnetic field. Often, the current in the output coil is integrated, yielding an output analog voltage proportional to the magnetic field. A wide variety of sensors are currently available and used to measure magnetic fields. Fluxgate compasses and gradiometers measure the direction and magnitude of of magnetic fields. Flux gates are affordable, rugged and compact, with miniaturization recently advancing to the point of complete sensor solutions in the form of IC chips, including examples from both academia and industry. This, plus the typically low power consumption, makes them ideal for a variety of sensing applications. Gradiometers are commonly used for archaeological prospecting and unexploded ordnance detection, such as the German military's popular Förster. The typical flux gate magnetometer consists of a sense coil surrounding an inner drive coil that is closely wound around a highly permeable core material, such as mu metal. An alternating current is applied to the drive winding, which drives the core in a continuous repeating cycle of saturation and unsaturation. To an external field, the core is alternately weakly permeable and highly permeable. The core is often a toroidally wrapped ring or a pair of linear elements whose drive windings are each wound in opposing directions. Such closed flux paths minimize coupling between the drive and sense windings. In the presence of an external magnetic field with the core in a highly permeable state, such a field will be locally attracted or gated through the sense winding. When the core is weakly permeable, the external field will not be so attracted. This continuous gating of the external field in and out of the sense winding induces a signal in the sense winding, whose principal frequency is twice that of the drive frequency, and whose strength and phase orientation vary directly with the external field magnitude and polarity. There are additional factors that affect the size of the resultant signal. These factors include the number of turns in the sense winding, magnetic permeability of the core, sensor geometry, and the gated flux rate of change with respect to time. Phase synchronous detection is used to extract these harmonic signals from the sense winding and convert them into a DC voltage proportional to the external magnetic field. Active current feedback may also be employed, such that the sense winding is driven to counteract the external field. In such cases, the feedback current varies linearly with the external magnetic field and is used as the basis for measurement. This helps to counter inherent nonlinearity between the applied external field strength and the flux gated through the sense winding. Squid magnetometers, squids, or superconducting quantum interference devices, measure extremely small changes in magnetic fields. They are very sensitive vector magnetometers, with noise levels as low as 3 fdHz-1/2 in commercial instruments and 0.4 fdHz-1/2 in experimental devices. Many liquid helium-cooled commercial squids achieve a flat noise spectrum from near DC to tens of kilohertz, making such devices ideal for time-domain biomagnetic signal measurements. Surf-atomic magnetometers demonstrated in laboratories so far reach competitive noise floor but in relatively small frequency ranges. Squid magnetometers require cooling with liquid helium or liquid nitrogen to operate. Hence, the packaging requirements to use them are rather stringent both from a thermal, mechanical as well as magnetic standpoint. Squid magnetometers are most commonly used to measure the magnetic fields produced by laboratory samples, also for brain or heart activity. Geophysical surveys use squids from time to time, but the logistics of cooling the squid are much more complicated than other magnetometers that operate at room temperature. Spin exchange relaxation-free atomic magnetometers at sufficiently high atomic density, extremely high sensitivity can be achieved. Spin exchange relaxation-free atomic magnetometers containing potassium, cesium or rubidium vapor operate similarly to the cesium magnetometers described described above, yet can reach sensitivities lower than 1 FDHZ-1/2. The surf magnetometers only operate in small magnetic fields. The Earth's field is about 50 micro-T. Surf magnetometers operate in fields less than 0.5 micro-T. Large volume detectors have achieved a sensitivity of 200 at Hz-1/2. This technology has greater sensitivity per unit volume than squid detectors. The technology can also produce very small magnetometers that may in the future replace coils for detecting changing magnetic fields. This technology may produce a magnetic sensor that has all of its input and output signals in the form of light on fiber optic cables. This would allow the magnetic measurement to be made in places where high electrical voltages exist.